My name is Erin Good. I'm chairing the IRENA Seminar Committee, and I'm really excited to introduce Marco Pignatari today. Marco got his PhD diploma at the University of Torino in 2006, studying S-process in massive stars. He was then a postdoc fellow at the University of Kiel, working with Falk Herwig and Michael Wiescher. He was then a junior researcher at the SNSF Fellowship at the University of Basel in Switzerland from 2010 to 2014. He then moved on to a postdoc at Core-Collapse Observatory in Budapest in 2015 with Maria Lugaro. In 2016, he started as a lecturer at the University of Hull and joined the Milne Center for Astrophysics. That while there, he became a senior lecturer in 2018 and a reader in 2019. And in 2021, he went back to work as a senior research fellow at the Core-Collapse Observatory again. So today he's going to be telling us all about the N process, which I know I've heard a lot about, but don't know much about. So take it away, Marco.
Thank you very much. Can you hear me?
Yeah. Yes.
Okay, good. So thanks for the opportunity for presenting this work. And lately there has become more and more, there's been more interest about this process, about this N process. And there's been also some confusion about it as well. So hopefully about what it is about. So hopefully this will be a really good opportunity to remove some of this confusion and explore a little bit why I think this is actually a really fun process to work with, and actually really interesting from the possibility and the potential that may have in terms of the information that may provide about Core-Collapse Supernovae. So I changed the slide. Did you see my slide? Are you seeing my second slide movie? I'm just checking. Can you see my second slide now?
Yeah.
Okay,
Yes.
great. So just to put into the context here in this, I just want to present within the neutron-capture processes where the N process is. And we start at the bottom with the lower neutron density. So the slow neutron-capture process where the neutron density can reach up to typically few 10 to the 12 neutron per centimeter cubed in massive star, a little bit lower for low mass UGB stars. But this is the S process, is really well known, it's a classical process, really well defined. And at the top here, at the top of the page, there is the R process where neutron densities are much larger than 10 to 20 newton per centimeter cube. And this is also really well classically defined and known. But in between, it's not that in star there is nothing. It's not that the other processes with intermediate neutron density are not happening in stars. So we start, there are different. So the neutron D2 alpha N can actually power in massive AGB star and super AGB stars neutron density higher than in the lower masses AGB stars. They can go up to, let's say, almost reach 10 to the 14 newton per centimeter cube, so they can go a little bit higher. And then there is between 10 to the 13 to 10 to the 3, up to 10 to the 16 newton per centimeter cube. There is the intermediate neutron-capture process, or I process. This also became really famous again in these last years. And this is related, this is following hydrogen ingestion in convective helium burning in different type of stars. And in between the intermediate neutron-capture process and the R process, in terms of the neutron density regime, there is the N process. And this is associated to the explosive helium burning Core-Collapse Supernovae. So this is the process I will talk about today. And so the N process was classically introduced from the work of Blake and Schramm in 1976 as the possible alternative to the classical R process. In this work, there was not associated a really specific neutron source or or source. It was associated, well, it is mentioned in the paper, if you go and read it, that is possible, has a possible stellar sites, Core-Collapse Supernovae or novae. And the interest was that you let him run the calculation for this regime of Newton densities. It was possible to produce elements all the way up to the actinides, and so they were proposing this as an alternative option compared to the more classical R process. A few years later, actually came in 1979 and beginning of 1980s, it came the work of Friedel, and then the work again of Blake Schramm together with Woolsey and Weaver, when they actually find that in a Core-Collapse supernova explosion, there is a specific part of the ejecta, external part of the ejecta, where there is explosive agent burning triggered, where the neutron-2012 fan can power Newton densities that are that can be associated to the end process regime. So the main conclusion that they reach in this work, again, try to reach, we did historical excursus to try to reach where we are today, but at the beginning there was proposed that this could be an alternative source of the R process. Well, these works that followed the initial proposal of Blake and Schramm say, well, this is not a source of the R process. So it's not possible to produce efficiently a process element. They found the Newton source, the Newton-2012 fan, the condition, but it was not possible to make the R process with this with this astrophysical source. So this snapshot, I just want to show here, how does it look like when if you run with a network with these typical Newton densities? How does it look like? What are the relevant reaction rates? So the isotopes that are made in the flow of the Newton captures are really close to the value of stability, not as far as the R process, of course, so much closer to the value of stability in between the S and the R process. In this sense, the isotopes that are populated are really similar to the intermediate Newton capture process. But the flows, the nucleosynthesis flow of the reaction rates, it actually looks really different compared to the intermediate Newton capture process. Here we can see that there is, in the panel at the bottom, there is a flow of Newton capture reactions that leave the value of stability, feed the unstable isotopes, and then they will later, once the end process is done, they will later feed by radiogenic decay the isotopes. So this is an explosive process. Typical time scale available for the end process to happen is, let's say, 1 second. So the temperature rise, the Newton density rise due to the Newton-2012 fan, the Newton capture is happening, and then after about 1 second, it's the activity is gone. But that's enough to activate a really interesting nucleosynthesis. That this is what I will talk about. So for this, we can already say, okay, what are the relevant reaction rates for the end process? Well, these are the N gamma rates, Newton capture, in particular the N gamma reaction rates that are going to be relevant to define what isotope are going to be produced. Mostly has radiogenic contribution. So, okay, the impact on galactic chemical evolution is not expected to be relevant because it's not really a strong Newton exposure associated to it, when material like it's happened for the S process or the I process. It's not like we start from the iron and we build up all the way through to heavier masses. It's more like a local type of process. But and this is why this process is so interesting. There are actually observables where you can directly compare to the results of stellar models. And these are presolar grains for Core-Collapse supernovae. Certain type of presolar grains, in particular carbon-rich presolar grains, they carry the signature of this process. And I will talk about this. And then also this process is really important for the contribution of the short-lived radioactive isotopes. By short-lived, I mean here between 0.1 and 100 million years. So some of them receive an important contribution for the end process, and some of them are the one that are measured or in for the signature is measured in the solar system. So how much the models make via this process is important, because then this information can be compared to this observation in the early solar system. And I will also talk a little bit about this. So I will start with the presolar grains applications. First, a couple of slides where I just briefly introduce what presolar grains are. So presolar grains, when stars die, they don't eject only gas. Some of this gas is condensing and from presolar grains. And some of these presolar grains live long enough that manage to enter in and be present in the molecular cloud when just before the solar system formation, the solar system formed. Presolar grains get trapped and captured in meteorites, and in meteorite get preserved for billions of years until this meteorite fall, and by a number of processes, the presolar grains can be selected away from the rest of the meteorite and can be analyzed in laboratories. And the different type of star, the different type of presolar grains are found that are made from different type of stars. Core-Collapse Supernovae is one of them. Of course, there are other type of grains from AGB stars, from nova maybe for neutron-capture supernova, but we'll focus in particular about presolar grains from massive stars here. So the picture is this. So when we can imagine, of course, we cannot observe anymore the supernova that form those presolar grains that are found in meteorites, because those supernova exploded 5 billion years ago, so we cannot see anymore. But these relics from those old explosions are found in meteorite and then can be analyzed. And by working with the idea that supernova that exploded 5 gigayears ago were not so different from the supernova that are exploding now, for the Core-Collapse supernova that exploded at the beginning, in the early stages of the galaxy. By studying these presolar grains, we can learn and get information about how Core-Collapse supernova explode, what they make, and then so apply what we understand from grains to many other applications that can go from galactic chemical evolution and general observations. So in this slide here, I show a general structure of a one-dimensional explosion, how a one-dimensional explosion look like. So there is still, this is a 15 solar mass, so there is still some hydrogen-rich envelope, and then there is a region where was exposed to the hydrogen fusion, and then to a little bit of helium fusion, that was the helium shell, and then there is the region that is where the carbon shell was, and then as soon as we move toward the center, we go in a smaller region where squeeze the product of the explosive oxygen fusion and explosive silicon fusion, so where the bulk of iron is. For the grains that we care about here, we care about the grains made in the helium shell, where the end process is also. And if we look at where the ejecta of the Core-Collapse supernova are carbon rich, so they're basically carbon rich only in the products, only in the ejecta of the helium shell. So, and this is really useful for what we are saying here, because this means that the carbon-rich presolar grains that are found in meteorites, and that we can say that they're coming from Core-Collapse supernova, this means that they will came from this region here. And this is the reason why, although the end process is not so relevant, for example, for galactic chemical evolution, presolar grains coming from this region will carry the signature, will be an ideal tool to actually observe the product of this specific region where the end process is taking place. So there is a selection there going on, and actually the grains are made from that region specifically from where the end process take place. As I said, there are different types of presolar grains. Actually, the majority of carbon-rich grains are coming from AGB stars. But if we look at isotopic ratios, and here, for example, there is carbon isotopic ratios versus nitrogen isotopic ratios, is possible to identify, due to the really strong isotopic anomalies, to understand or say that specific single grain from what source was coming from. For example, typically, if we look at the presolar grains with nitrogen 15 enrichment compared to nitrogen 14, they typically come from core-collapse supernovae. While if we go above, and so nitrogen 14 rich grains, then there is a possibility of contribution mostly from AGB stars or post-AGB stars. But by looking at the isotopic ratios, that is not heavy elements, it's possible already to say what is the source of this grain. And then by knowing that grain, where it's coming from, then one can go and look after the heavy element signature and see what is observed in there. So, as I said, the presolar grains, in particular, carbon-rich grains, in particular, what I call here X grains. So X grains, keep in mind, about only 1% or anyway, a small fraction of all presolar silicon carbides are coming from core-collapse supernovae, but they can be identified. And it's possible for some of them, not enough, but for some of them, the heavy elements were measured. And when I say heavy elements, I'm not meaning here the elemental abundance. Here, I mean the isotopic abundance for those given elements. So for few of these silicon carbide X grains, they were measured strontium, zirconium, molybdenum, ruthenium, or barium. So there is information about the isotopic pattern for these specific elements. And in the moment that we have isotopic abundance available, it's really possible to find a lot of information, because it's in the moment that we look not at the elemental ratio, but the isotopic ratios, it becomes way more difficult than for stellar simulation to fit the pattern that is observed. And what was anomalous about this pattern observing those grains is that it wasn't looking like S process, and it wasn't looking like R process either. Since this first measurement here, for example, from Pellin et al. 2006, molybdenum, for example, molybdenum S process, a typical isotope of molybdenum is molybdenum 96. Typical R process isotope of molybdenum is molybdenum 100. Well, they are not enhanced in this type of grains. Molybdenum 95 and 97 are enhanced. So this is the signature observed is definitely not S or R process. And then Mayer et al. In 2000, just he showed that, okay, this signature, it's compatible with neutron densities typical of the neutron burst or of the end process in the explosive helium shell, as it was expected since those grains were coming from that region. Actually, in a few years ago, we looked into this in more detail, and the picture is a little bit more complicated than that, because in reality, first of all, there are slightly different signature in these few presolar grains that we have, but it's not a specific neutron density that is given this result of, for example, for molybdenum, high molybdenum 95, high molybdenum 97. But in reality, it's a contribution. It's coming from the contribution of different zone in the shell. So we have a shock wave hitting the bottom of the helium shell and proceeding. And so when we do the simulations, there is hydrogen of zone calculated from at the shockwave passage, and some zones are enriched in molybdenum 100, some are enriched in molybdenum 95, some enriched in molybdenum 97. So what we obtained here I just zoom when there is the models are compared with the presolar grains. The result of this, for example, 95 and 97 enrichment is the result of a contribution of different regions of the shell that ended up generating the 95 and 97. So instead of being a one specific neutron density, is a composition of different part of the helium shell that when we put them together, it gives the 95 and 97, molybdenum 95, molybdenum 97 enrichment. So this means that the information that we get is not on the neutron density itself, is giving information, for example, of how strong was the shock in the helium shell. For example, here, just to clarify this point better, I show another model, not the one showed before. So it's a 15 solar mass. And here I zoom in this region at the bottom of the helium shell where the peak of the neutron burst is hitting. So if we look at the 95, first of all, there is a lot of structure. There is a lot of secondary peaks here. And that's because there is the direct contribution and the radiogenic contribution from different isotopes. But we can see here that there is, for example, here, the enrichment of molybdenum 95, but the enrichment of molybdenum 97 here in dashed line. So there are certain regions here where it's more enriched in 95, other region that is more enriched in 97, and then there are other regions where there is also a contribution from molybdenum 100. So if the shock is not strong enough, you would have no enrichment in molybdenum 97, for instance, mostly on molybdenum 95 because it's lighter, so it's easier to enrich by the end process than molybdenum 95. So since we have this double peak 95 and 97 is telling us an information about how strong was the shock at the bottom of the helium shell. So so using this approach is actually, it's starting telling us information about what were the conditions at the bottom of the helium shell of that Core-Collapse Supernova that exploded 5 gigayears ago, that we don't know the mass, we don't know the explosion energy, anything, but we can gather information about what were the temperature peak and the density peak when the supernova shock hit the bottom of the helium shell. So there is also some S process signature in here. For example, you can see molybdenum 96 that was enriched here, increase in the upper part of the helium shell, and that's because there was some small S process going on in the shell before the explosion. But then the molybdenum 96 is destroyed from the end process, and so that's why those grains are enriched in 95 and 97 and not in molybdenum 96. Okay. So this about molybdenum, but the really interesting part, so that there is other interesting things about those grains. So it's not find the signature of the end process only in heavy element, but it's possible to find the signature also for lighter isotopes. Here there is the case of silicon-32. A few years ago, there was a big problem because when there were found some type of grains, not the silicon X grains, but another rare type called 6C grains, where they were enriched in sulfur-32, but there was no enrichment in silicon-28, only in silicon-29 and silicon-30. And this was puzzling because silicon-28 is made together with sulfur-32, or better, the bulk of silicon-28 is made together with the bulk of sulfur-32 in Core-Collapse Supernovae in explosive oxygen burning conditions. So it was really puzzling to see sulfur-32 and not silicon-28 there. And then when we looked into this, we say, hang on, but there is a neutron burst there, there is the end process. And here, right after silicon-30, along the neutron-capture path, there is silicon-31, and then silicon-31 is doing silicon-31 and gamma, and is produced silicon-32. And silicon-32 is 130 years, has 130 years half-life. So when the grains will form after the explosion, few years after the explosion is done, silicon-32 will still be silicon-32 and will condense in silicon carbide grains, has silicon really efficiently and not as sulfur. So this is why actually we expect to see the strong enhancement in sulfur-32. That was silicon-32. And so this was confirmed also from later nanoseams analysis, where by looking at grains, it was possible to identify regions where there was sulfur-32 with basically no sulfur-34, excepting on the external part. So when we look at this delta, here it is, this plot here is using delta notation, means variation per mil. So delta sulfur-33 means variation per mil with respect to solar of sulfur-33 over sulfur-32, and the same here for sulfur-34. We can explain in this diagram grains like this one down here, minus 1000 it means that it's pure sulfur-32. And again, from the nucleosynthesis point of view, it's impossible, accepting that we accept that this was formed as silicon-32. Silicon-32 condensing grains way more efficiently than sulfur, actually 4 orders of magnitude more efficient. And then this is why we can explain this incredibly high abundance of sulfur-32 compared to the other sulfur isotopes in grains. And again, silicon-32 was a product of the, in these grains, of the neutron burst, of the end process. Problem, and this is something that we looked into this, again, I was in Basel back then, we looked to this with Friedel and Tommy and many others. The problem is that silicon-32, this N gamma rate is actually, well, what we have, we use what we have when we do nucleosynthesis calculation. And what we have as a flashback reaction rates, but the problem is that those models are not really applicable in those, for these isotopes. So here, in 2013, for example, we compared the value of the reaction rate using 3 different Hausser-Feshbach models. There was variation in the order of factor of 2 orders of magnitude. And this is affecting the predictive power of the models. And in this plot here, I show why it's actually important to know really well those cross sections. So there are 2 models here, well, 4 models, but 2 models with 2 different energies. The continuous slide. So let's, for example, take this model here with a peak here where my pointer is. And then there is another peak here. Those 2 models are models with 2 different explosion energies. So a stronger explosion energies to the peak of silicon, this is silicon-32 over silicon-28. So we look at the ratio. So if we have a more energetic explosion, the peak is translated a little bit outside, but the height of the peak of the ratio is not changed. Right, so we reduce the energy, the peak is gonna, if we still reduce the energy, well, you don't have any more silicon-32 produced in the carbon-rich region. This is what you want if you wanna observe it in the grain. What the cross-section are doing are changing the height of this peak. So I keep the energy of the explosion the same, I change the cross-section, in this case, just silicon-32 and gamma, and the peak is going down. And why we care about this, why we care about this, the height of this peak? Because we have this kind of orange band here, and that's the range of silicon-32 of silicon-28 measured in grains based on the sulfur-32 over silicon-28. So it's possible, it's okay, this was the abundance, this was the original ratio of silicon-32 over silicon-28 expected to be in the ejecta of the helium shell that made those grains. So now you can see here that, yes, the explosion is telling me something, but at the end of the day, it doesn't change my peak. If I know what is the ratio, and I need the cross-section for that, I know things, for example, how much was diluted the grain with normal material without silicon-32 in order to fit the grains. It's good if the models are above this band, but it's bad, of course, they are below, because this means that we cannot fit those silicon-32 enrichment. So here again, a snapshot when you see the different peaks, the production, typical production of the neutron-capture flow along the N-gamma sequence of capture, starting from silicon-30, that is this black line here, and then is producing silicon-31. Silicon-31 is doing N-gamma and is making silicon-32. That's discontinuing, but it's fading down, right? Because there is not much time. In a second, it's done, and then there is no the neutron-22 alpha doesn't work anymore. Until here, just plot until silicon-34, but then you would see going down and down and down in the production. And how far you go, how much silicon-32 we make, depends on silicon-31 and gamma, and silicon-32 and gamma, but that we don't know much, or they are poorly constrained from the model yet. So there is definitely needed from the experiment. And I'm trying to go a little bit quicker now because I want to go to the second phase, but here I just want to mention that in the past years, there was So actually, the end process is really relevant, and this is really relevant also for novae. And this is relevant for novae because in the past year, there was a lot of few experiments related in the sulfur region, so sulfur 34p gamma, chlorine 34p gamma, with the idea that the sulfur isotopic ratios can be used to disentangle if the some grains are coming from novae or are coming from core-collapse supernovae. However, this problem of the silicon to sulfur fractionation, this production of silicon-32, is making really problematic. So you cannot just use sulfur alone to say if a grain is coming from core-collapse supernovae of novae. And this is a student project that actually I did also about this a few years ago when I was still in Hall, and a secondary school student. And the student actually looked at the different models. And this plot is really representative because it shows the sulfur 34 for sulfur 32 when it's considered, where we don't consider the fractionation, where we consider the fractionation. And in this, there is embedded a lot of uncertainties. How much is the strength of the shock? How much is the end gamma? What are the end gamma uncertainties? But typically nova grains are around here that are right in the middle of this big variation region. So definitely you cannot use just the sulfur isotopes because of this to identify they are from nova or not. Okay, I just quickly mentioned that actually not all the presolar grains for core-collapse supernovae, carbon-rich presolar grains for core-collapse supernovae, they carry the signature of the end process. And that was really cool. There is a recent work from Nan Liu and collaborators 2019, when they measure from silicon carbide AB1 grains, so those grains here, with enriching nitrogen 15, that now we understand that they are for core-collapse supernova, they measured the heavy elements, and in this case there is molybdenum and barium, and they're reaching the S process. There is no N process, and we understand this when we predicted that this was the case because these grains here, this specific type of grains here, they carry the signature of the hydrogen ingestion. They progenitors were affected from hydrogen ingestion. Just before the supernova exploded, there was some hydrogen alive there. The shock hit it. It produced the nitrogen 15 that we see in these grains, but this hydrogen didn't allow the neon 22 plus alpha to work. Because if there is just a little bit of protons around, the neon 22 want to capture those protons and not the alpha particles. So the neon 22 is capturing the proton, is not burned from the, is not doing alpha N, and so there is no N process. And this is why in those grains we see the S process signature that is typical for the, more typical of the, so the end process is more typical to silicon carbide X grains, but instead we see the previous, the pre-supernova S process signature. So those grains, this process, hydrogen ingestion and the shock following, it's really good to make a lot of aluminum 26, but it's not really good to make the end process and or produce iron 60, for example. Okay, so talking about iron 60, in the last 10 minutes or so, I want to discuss a little bit about the short-lived radioactives. And here, I just want to mention in the early solar system, here I just want to mention a really good review that Maria Luger did in 2018, where there is a really good summary of what the status of the observation of these, what they are. And we can learn a lot by looking at these type of isotopes. These are typically the half-life between 0.1 and million years and 1 million years. So they were around, some of those were around when the solar system formed. And of course, it's not possible to measure them directly, but it's possible by looking at the isotopic anomalies to measure and infer some of them were around when the solar system formed. And the interesting part is that when we actually, many of those are made in core-collapse supernovae, are made together in different parts of the core-collapse supernova ejecta. So by looking at the pattern of these isotopes in the early solar system, it's then possible to go infer and understand if there were, if, for example, a Core-Collapse supernova exploded nearby the solar system, well, nearby the cloud that from where the solar system formed, it's possible to understand if the pattern is consistent or not. So there's different issues. There are a lot of things involved in this analysis, but there is a lot of those isotopes that are made in the helium shell and actually made from the neutron burst. And I want to focus a little bit on those now. Ion 60. So ion 60, in particular, if we go to the lower masses, lower massive stars, so the 15 solar mass, for example, their production tend to be dominated, for ion 60 tend to be dominated from the neutron burst. So you see this really bright peak here in the abundances. Mostly is directly as ion 60 itself, but there is also here secondary peak made as so here this is interesting because you see this kind of double peak here where the neutron burst is too strong and is destroying ion 60, right? So this is the neutron burst can be so strong that doesn't have to stop at ion 60, it can also go beyond. But anyway, so ion 60 is made. If you take heavier masses, the ion 60 can be, maybe the production can be dominated from production in deeper ejecta in the carbon shell. But for this model, for example, we can see that the production in the carbon shell is extremely smaller compared to the contribution from the end process at the bottom of the helium shell. So the ion 60 is the most famous, if you want, one of the most famous short-lived radioactives, aluminium-26, the other is ion 60. Ion 60 received a really important contribution from the end process. And here I just want to mention that one of the bigger uncertainty about the production of the ion 60, of course, is that before reaching ion 60, from ion 58, we do a neutron capture on ion 58. So ion 58 and gamma, making ion 59. Ion 59 is doing another neutron capture and is making ion 60. And of course, there was a lot of experimental information about ion 60 and gamma available, but not much about ion 59. But with this recent work from Jan et al. In 2021, it was possible, those data, there was an evaluation and an estimation of ion 59 and gamma with way smaller uncertainties compared to typical theoretical uncertainty. And in this calculation we did, for example, here you can see the variation in the yields due to the uncertainty of the ion 59 and gamma. So here's the variation, the ion 60 yields for three explosive model and the two Core-Collapse Supernova progenitors looking before the explosion. And with this cross-section, the typical impact of the ion 59 and gamma uncertainty goes down to 10 to 20%. So the ion 60 and gamma is probably, well, start to be well constrained. The ion 59 and gamma now apparently is also well constrained. This means that here the major uncertainty could be only the stellar uncertainty. So this is actually a really fantastic contribution that nuclear experiments can give. So reduce their uncertainty as much as possible from the experimental analysis, and then stellar modelists can focus in the impact of stellar uncertainties, and then use this to study the production of the ion 60, but with more robust prediction. It's not only ion 60 that is interesting. Here, for example, I mentioned iodine 129. Iodine 129 is considered to be a typical short-lived radioactive product of the R process, but also the N process can make it. So you can see here again at the bottom of the helium shell, there are a few peaks. Mostly is made in this case for this model has antimony 129 and tin 129. while the production in the deeper part, like in the carbon shell or in the deeper part of the ejecta, is negligible. So there is a production, and for this case of this specific isotope, again, this is not our process, this is end process production. This is dominated from the end process for this specific model. Another isotope here, cesium-135, and here we can see that the production of the end process in this case is more comparable to the production of by the S process in the carbon shell. And here again we have a significant structure, complex structure here, where we have a peak that has radiogenic contribution for xenon-135, and then another broader peak from iodine-135, and then here another peak for tellurium-135. Again, here, this is a model with a given energy, but then really important things to take into account here. What is, for example, the impact of the neutron capture uncertainties, or the N-gamma reactions uncertainties they may have in this picture? Of course, the production is going to be affected from these uncertainties. Okay, is this any relevant compared to the other radioactives? So in Lausanne 2022, we have done a work where we have looked at the different core-collapse supernova masses, not only produced from us, but produced from other groups, for Rauscher 2002, from Curtis 2019, Cervedi 2018, Limongen, Kefi, and so on. So we have compared the production of all the short-lived radioactive that are measured in the solar system, and now with the work that we're doing, again with Thomas, we are preparing, we are taking all this data, and we are normalizing. We are normalizing distribution to aluminum-26, and after a given isolation time of this isotope, we are checking how the distribution look like. Well, no surprise, there is a strong iron-60 overproduction compared to aluminum-26. This is known and written everywhere in the literature, but the same is true, for example, for cesium-135 and others, while, for example, the production of iodine-129 is in line with the production of aluminum-26. Again, here, I'm going really quickly about something that would require actually a full seminar by itself, but it's really interesting because actually, even considering all of these different models, if you're considering iodine-129 over aluminum-26 production, all these models seems to be really consistent to say that there is a relevant production of iodine-129. And this production is really important because if, for example, here just provide two reference for you to go and check, iodine-129, well, together with other short-lived radioactive like curium, for example, has been used to calculate the isolation time, how much time it passed between the last process event and the formation of the solar system. And from the past analysis like Cote et al. In 2019 or Banerjee 2021, by using iodine-129, there is this typical waiting time between 80 and 120 million years. But as Banerjee say currently in his paper, well, this depends also in how many sources are, what they produce, and the only warning or caveat here that we need to be careful is that the end process could be produce one of these sources, one of these extra contribution to iodine-129 that could make all of these analyses more complicated. So I will finish, I'm done. I just want to quickly mention here is that nuclear uncertainty studies for the end process, I'm going to go really quick here because there are no specific nuclear sensitivities uncertainty studies available done for the end process. Although we expect, we need to check, but there's probably going to be some overlap about relevant nuclear uncertainties for the I process. And for this, there are more studies in the past year, but definitely something to look into because it's going to be important to understand all of these different radiogenic contribution. We saw for presolar grains, for example, what are the N-gamma rays that are relevant for the production of molybdenum-95, molybdenum-97? Right, because these are going to be extremely important to understand this double peak production and then have a robust prediction about the dependence of these two peaks with the energetic of the shock at the bottom of the helium shell. The only impact, I mean, an impact study that we did, but was really basic, was changing that 10 years ago for the silicon-32 case when we analyzed the impact of the silicon-32 and gamma, and then we did someone for silicon-31 and gamma, but it was really, really limited. So definitely something that would be good to have is to design and develop a number of sensitivity study and see what are the N gammas, because those cross sections can be experiments can be done to constrain better those cross section. The same regime that has been explored now for the I process. So definitely it can work also for the N process. Okay, so this is my summary. The N process is classically is there from decades, and it's really interesting because it's not affected by the stellar uncertainties that the S process or the I process have, how the carbon-13 pocket form for the S process, or the drastic dependence that the I process prediction have from multidimensional hydrodynamic simulations. But it's closer to the value of stability, so it doesn't have also the big nuclear uncertainties that really challenging nuclear uncertainties to tackle that the R process has. And the cool thing is that they are observable, but they are isotopic patterns. So this is what they make really constraining. And for presolar grains that can be measured in laboratories, can be measured really accurately. I mentioned about a few cases for the presolar grains, and then I mentioned about their production for the Shirley radioactives that are actually going to be really important. I didn't mention it here. It's something that actually we are looking into, but of course, from different models, they're going to be different end process signatures, depending if we compare, for example, progenitor with the same initial mass, they're going to be big differences depending in what happens before during the evolution and in the type of explosion that is done on top of the progenitor. So that's also another interesting aspect not to forget. But in particular, I mean, we have those grains, we have really few measurements available. So definitely the potential that the presolar grains have here, using the N process, having more presolar grains measurement would definitely provide a really powerful diagnostics for Core-Collapse supernova explosion. Without the large complexity about, it's not like the production of the ion group really that is really close to the more extreme part of the ejecta, where this type of supernova engine or the complexity of the explosion are going to play a major role. Here we're in the external part, so there is really like the shock passing and hitting. So there is, in a sense, it's easier to get information about what were the conditions in those external layers. So again, it's a really fun process to look at. There are observables. It's a major need of doing to get experimental data to constrain the relevant neutron-capture cross-sections. And again, this is something that require larger collaboration and collaboration between different groups, and requires a lot of share of information. So here I just mention IRENA and NuGrid and JINA and Tech Infra and Kampan that are like these networks and collaboration that can align these and work in these processes where stellar physics is important, but also nuclear physics and observation. So this is a real an ideal topic to study for these for our collaborations. Okay, thank you. I finished.